So what I'm going to cover today, and I know you all have a diverse backgrounds, right? So some of this might be just review for you guys. It might be oversimplified for some of you. It might be new to you. But I'm just going to talk about unit economics in general for manufacturing or production, right? And a power plant is really just a factory producing electrons, right? So whether you're producing, you're thinking of concepts for power production, or if you're thinking of concepts for maybe a product or component that has to be manufactured, these concepts will be useful. So I'm going to cover unit economics, so the cost of electricity. You know, I'm sure you guys have all seen at this point, you know, estimates for levelized cost of electricity, or just what does it cost cents per kilowatt hour. There's so many numbers that go into that. There's a lot of times it's really sort of daunting to try to dig into it. So I'm going to try to make it super, super simple, and by oversimplifying. Okay. Then I'm just going to go into one simple cost model from MIT, and just sort of talk about the line items that are in that spreadsheet, and just to make sure you're familiar with. You know, a lot of you may already be familiar with those things, but we'll just talk about the units and what those terms mean, so that when you want to look at analysis of electricity cost, you're sort of familiar with those terms. And then finally, I'm just going to go through sort of like the steps of how you start from a blank piece of paper to get that back of the envelope calculation for your idea. So the goal of this is just to basically give you some tips and tools for making very simple back of the envelope calculations at the idea stage. Okay, so this is Thomas Edison's estimate for his first power generation station. Okay, it's really interesting because it's pretty simple, right? You can look at these things, you probably understand what those words mean. It's basically capital investment, the power plant building, boilers, steam engines, auxiliary electrical equipment, meters. Then he has labor, just all the different labor, and then, you know, then he has rent. I'll talk a little bit later about depreciation. But the point is that this is probably more complex than you'll need to get just to have a conversation with someone about the cost of your idea. So, I think it's worth repeating. Like, the point of a business is to make money. Sell it for more than it costs to make it. Particularly for commodities, it's pretty simple to know what price you're going to receive, but it's a lot more complicated to understand what your real costs are going to be. So, the idea is, ideally, you'd be like Pokemon Go, right? It costs for nothing, and you're like raking it in. And if you're not, you're a zombie. So, before I go into into the economics, if you're going to make a cost model, and if you're going to look at other cost models, it's useful to know sort of there's a hierarchy involved, and there's multiple layers, and it's useful to know when you're looking at a number which layer that fits into. And this is also sort of the order of operations that you would go through to estimating the cost of your thing. So the first is just a basic bill of materials. This is often, more often used bill of materials in a device manufacturing concept, right? Like, so if you're, a lot of my background is sort of more chemical process stuff. Bill of materials is a list of all the materials that end up in your final product, right? So if you're coming up with a cost estimate for a nuclear power plant, you're not going to probably do a bill of materials because, well, at the construction phase you would, but you're producing electrons, so that's not a term you'll see very often. But if you're manufacturing a device or a component, that's an important thing to have. And then a process flow diagram, right? Just very simply, what does the process look like? The steps that you're doing to construct or produce your product. Then outside of that is a production cost model. This is where you assign economic values, right? So after you start with your bill of materials and your process flow diagram, you then assign operations costs, right? These are the costs associated with the materials that go into your product, the labor and the chemicals, and then the infrastructure costs, right? I often just think of it as a box and an arrow going through, right? What's the cost of your box, and what's the cost of all the stuff that's going through it? And then outside of that, right, is a financial model. And this is where things get dicey, I think, and where it often stops people from going further, because the investment analysis, the cash flow, the financing terms, the rate of return, these are all numbers that are variable depending on, there's a wide range of assumptions with these numbers. And at the end of the day, they're important. They're part of the final cost of your product, but it's important to realize the difference between what's a financial assumption and what's just an assumption about the actual physical dimensions and parameters that govern your system, and to be able to tease those numbers out when you're looking at other people's numbers. So bill of materials is just, again, all the materials that go into your final product. It's also often called BOM. You only have people, if you're working with a contract manufacturer, it's what's your BOM. And it's just a list, and it's just a list of the stuff that goes into your product. Often with the quantity, the mass, and you might have a unit cost too. So again, it excludes process inputs. It's just what's in the final product. And a good first step, if you're thinking about producing a physical device or machine or something, is to look at your BOM and just ask, is the cost of the inputs lower than the price I want to sell it for? Getting accurate prices for like steel and chemical stuff is not always easy. To actually get those commodity prices often requires a little bit of digging, and what you might find it for retail is often, wholesale lower than that, but still, it's still a worthwhile exercise to go through. Next, process flow diagram. Now, a lot of you are engineers, so you know what a process flow diagram is, but for those of you who are not, here's a process flow diagram for washing your clothes. It's a very simple representation. It can be simple or complex, but it's really helpful to have a process flow diagram to anchor conversation when you're talking about, I want to produce something. This is often really helpful to have a very simple sketch and say, okay, here's this process, here's my assumptions about the inputs and outputs. This captures, there's a lot of other things I could put in here, like the power, right? I didn't put in electricity, but it's really good to start at this point. Now, I just Googled nuclear power process flow diagram, and I came up with a lot of interesting results. Okay, this is uranium mining and processing. All right, and actually, I think that's a really good one. It's super simple, and now I understand the process a little bit more. Anywhere from that simple diagram to a pretty complicated engineering process flow diagram. Anything like this can always be made more simple. Okay, and so I encourage you, even if you have something that's complicated, to keep it simple at the idea stage. Okay, so now I'm going to sort of walk through. Remember when I said in that production cost model there was the operating cost and the infrastructure cost? I like to keep it always in those two buckets, right? There's a lot of ways you can slice the pie, but the way that I think about it, I think the way is simple to think about it, is just OpEx and CapEx, okay? So what is OpEx and CapEx? OpEx, and these are sort of the shorthands that you'll hear finance people use a lot. OpEx is operating cost. It's operating expense or operating costs. It's materials, labors, fuel, utilities, waste removal, etc. All those costs, variable costs plus the fixed costs, that are usually represented on an annual basis. Now, CapEx, the infrastructure cost, Here are all the other words that you might hear instead of CapEx or capital cost. Capital expenditure, investment cost, upfront cost, overnight cost, especially with power plant construction, capital outlay, installed cost. It's just the upfront investment in infrastructure. Now, I want to point out here the units here are in dollars, not in dollars per year. So that's important. And I'm going to talk about, if you want to come up with a cost per unit, like what does it cost per widget I make or per kilowatt hour I produce? Well, your upfront cost is a one-time, or a one-time investment, but you can be producing for a known amount of time. There's so many assumptions and calculations that can go into that. At the end of the day, it's about the net present value of your investment in financing terms, interest rates, all that stuff. But you don't really need to know that to come up with depreciation. It's generally 10 to 15% to turn it into an annual cost. Okay, and we could talk about that later. But again, the goal of this presentation is to just give you the sort of like the quick and dirty tools and tricks for being able to come up with these back-of-the-envelope calculations. So now we have depreciation and OpEx on dollars per year. We can divide by the production per year to get the cost per unit. Now, another thing just to point out with power plants, you'll see this in cents per kilowatt hour, but you'll also see CapEx in dollars per kilowatt or megawatt, right? And it's important to not get those units confused. Cents per kilowatt hour is a unit cost, and cost per megawatt hour or kilowatt hour is a cost that represents the capacity of that factory or power plant to produce, right? And you'll often see, for instance, solar compared with nuclear or any other type of power source on a cost per kilowatt basis or cost per megawatt basis. Then that's confusing, and then you'll see, well, that's different than the cost per kilowatt hour, right? So why are those numbers different? Somebody say why those numbers are different usually? What are those things that make those numbers?
Well, the OpEx and the CapEx are different for each facility.
Right. For let's say solar and nuclear, right? What's one of the biggest components that makes the levelized cost of electricity different than? Sorry, so you had your hand up. All right.
Depends how long it runs for.
How long it runs for?
Producing solar for, I don't know, let's say 8 hours a day.
Okay.
Producing nuclear for 24 hours a day.
Right.
Then you're going to have, even if the rate for solar may look cheaper, you may not be producing it for as long.
Right.
So then it depends on the assumptions made.
Right. So even though, for instance, the cost of nuclear and solar on a dollars per kilowatt basis might look very much the same. Yes.
Isn't the point of levelized cost of electricity to remove some of those terms so that you can actually compare them better, or you have ways
Yes.
to compare for an offset? Because it's actually for a third, they're all evaluated, at least for the Energy Information Agency, they all evaluate on a 30-year lifespan with the upfront costs, fuel costs, maintenance costs. So it is kind of comparable because the capacity factor is accounted for in levelized cost of electricity.
Right. That all goes into levelized cost of electricity, but you'll often see, the cost per kilowatt or cost per megawatt is still a very, at least from what I've seen, still a very common way of characterizing different energy production technologies, right? Because it doesn't affect, for example, the amount of hours per day that a solar plant is running depends on the location, right? So when you do levelized cost of electricity, you have to make all those assumptions. So a lot of times it's helpful because it allows you to compare things across, but you also have to make assumptions about location, financing terms, and all this stuff, whereas the dollars per kilowatt or dollars per megawatt is like a pure cost of the technology by its potential to produce electricity. So let's go dig into that a little bit more, right? So here is the NREL's simple levelized cost of electricity formula. okay? So it's the capital cost times the capital recovery factor, which remember I said just use 10 to 15%. That's essentially the capital recovery factor. It's a coefficient that you're applying to the total capital cost to bring it in line in the same units with the O&M cost, right? Then divided by essentially how much electricity you're producing. So when I look at this, I see this still doesn't look simple. Okay, so whoops. So here's my super simple, even simpler levelized cost of electricity. It's just depreciation. It's your annual capex plus your opex divided by how much electricity you're producing. Okay, and it's helpful to keep that in mind when you're looking at other estimates. Okay, because you don't need to know all these numbers to be able to get I'd say order of magnitude, but to get a fairly accurate estimate of what the assumptions that are going into an estimate, someone else's estimate in particular are. So, going back to Edison's power plant, back of the envelope cost estimate, in the upper left is the capital investment, and then on the upper right, that's the depreciation, right? So this is how Edison pulled the capital cost into an annual cost, right? So if you look at some of the assumptions that Edison made and the depreciation, he's actually being very favorable to his economics, because the numbers, remember how I said it, like 10 to 15%? I think these numbers are based on the lifetime of the equipment, right? So if you assume no financing, whatever, you don't have to pay an interest rate on the money you borrow. At the bare minimum, you can assume that when you sort of reach a steady state, you're gonna have to replace the capital equipment as it expires or it reaches the end of the life. So at 2% for 3% for the steam engine dynamos, you can assume that he thought maybe the boilers and auxiliary equipment at 10% that they would be replaced every 10 years, or the conductors every 50 years, right? But now that $6,000 at the bottom, he adds to the operating cost here. See the line that says depreciation? So you can see how sensitive the total cost is to the percentages you applied there in the depreciation. Okay. This number, the total cost of this project was a lot different if he had used higher percentages for the depreciation. Are there any questions? Sorry, I haven't been giving you guys a lot of chances to ask questions about this. Is everyone on the page here? Okay, go ahead.
If you've got a boiler and it's going to last 10 years, for example, and we kind of know that's a service,
Yeah.
then surely that's not a terrible assumption. This isn't compound interest, this is just straight up interest.
Right.
It's like how much you pay for it over years. Yeah.
The-
So what I'm trying to understand is how I'm struggling to understand
Yeah.
why this is such a bad technique to say if it's going to last 10 years, you're going to pay that cost over 10 years, then you're going to replace it and start again.
Good
I don't see
question.
why it's not an issue.
Right, so why shouldn't we just divide by the lifetime?
Yeah.
Right?
Exactly.
Because you have to pay for that equipment, and unless you are independently wealthy, you're gonna have to borrow that money. And you're gonna have to pay it back over a period of time that's probably less than 50 years, all right? So this is sort of, I would say, this is still a good exercise to go through, because in the same way sort of that the dollars per megawatt or kilowatt represents like the physical constraints and the physical parameters of the technology, that represents the lifetime of the equipment, and it divorces that number from financial terms, which is again why I think it's helpful to think of those different layers, right? What's the actual physical system, and what are the costs associated with that based on the actual physical characteristics in the lifetime of the equipment versus all these financial assumptions which don't have anything to do with the technology. It has to do with the cost of capital, and it has to do with financial markets, right? And if you guys haven't read Empires of Light, it's a great book. It's all about Edison, Tesla, and the financiers that made it possible. Great book. I just finished it. Okay, so I just pulled this this chart from a paper looking at the cost of nuclear power. This is one representation of the components of the cost of a LCOE. Okay, couple things to note here. First of all, it's in 2004 dollars. You'll have to go back and forth if you're looking at other numbers. Just use the consumer price index. All right, it's a nice little calculator. Have any of you guys ever used it to convert numbers? Right, it's just the I think it's the Bureau of Commerce, the Bureau of Labor. It's just a nifty little calculator. You go on and you say 2004. $10 in 2004 is equal to how many dollars in 2007 or 2013? Okay. So if you want to compare numbers, you have to convert. It's a pain in the butt, but it's actually not really. It's easy, but you have to know how to do that. And so the consumer price index is how you would do that. So I would look at these numbers and I say, okay, the first thing I do is it CapEx or is it OpEx? Okay, so capital cost, well, obviously that's capital cost. Total O&M, that would be O&M, right? Reserve margin, I guess that's O&M. I'm not an expert on power markets, but I would also look at that and say, it's such a small number, who cares, right? Fuel costs, OpEx, right? Interest cost, CapEx. Including capital additions, CapEx, right? Decommissioning and decommissioning, I'm not exactly sure how I would put that in, but it's, again, I can't even see it on the graph. And decommissioning, by the way, is at the end of the project's life, and because the cost of money in the future is discounted, it's really minimized. Yeah.
I think, I don't know how to do it in the US, but in the UK they put the discounted rate into they legally have to put it into the capital costs at the beginning.
Oh, really?
Yeah. It pays for itself.
Okay.
Should.
Okay, that's interesting. And then waste disposal, that's operating costs. So again, I look at this and I just put it into those two buckets. And so again, if you look at these, it shows that these are, by the way, the three on the left are the three most lowest cost nuclear reactors in the United States. 3 to 6 cents per kilowatt hour versus some projected costs. So just to keep those numbers in mind, I'm sure you guys have seen similar cost estimates before, but I just want to go through, here's the EIA's Energy Annual Outlook projected levelized cost of electricity by source, 2020. So pretty much now, if you started to do a project now and it was, construction started now, this would be essentially current costs. So I just wanted to see if you guys maybe could guess what some of these technologies are. Yeah.
The yellow one's probably offshore wind.
Close.
Onshore.
I'll give you a hint. The light blue is wind. Which one's onshore and which one's offshore? Yeah. I'll give you a hint too. The colors, I sort of tried to use color code by.
Black is like coal. Is black coal?
Black is coal, yeah.
So green might be nuclear.
No.
Well, those are close. Green is biomass.
Is nuclear red?
Nuclear is red. Yeah. So there's where you are, right? It kind of in the middle. These, by the way, are all natural. The orange is all natural gas. Yellow is solar PV on the bottom and solar thermal on the top. This is hydroelectric power. Why do you think hydroelectric power, if you guys are like, hydropower is one of the cheapest sources of power there is, but it doesn't look like that here. Why do you think?
Tap most of it.
Pardon?
We've used most of the available practical hydropower in the world.
Right, but existing existing hydropower plants can sell their electricity for like 1 cent a kilowatt hour.
High capital cost?
It has initial, exactly. Most of the hydropower plants are like at least 50 years old, or it's all been paid off, right? There's no fuel cost, and so that's again why the time is always, even though the cost of the technology has nothing to do with time, you can't divorce the time component from the levelized cost of electricity because it has to do with financing. Yeah.
Just a quick clarification, on either side of the natural gas column, it looks from here like there's a black one and then a lower black one. What are those two sources? I think we said.
That is actually, I guess I made that brown.
Okay.
So can you guess what it is? Brown.
Geothermal?
Geothermal, yeah. So, right, so why don't we have geothermal everywhere? Well, because that's location constrained, right? So, here, now I put them all on, actually you can see that. Now, the next thing I'm gonna do is show the gray data points are capital costs, okay? So the fraction of that cost of electricity, that's capital cost. And I think this would be if you built a new hydroelectric facility, okay? So if you guys are thinking about nuclear concepts, here's sort of your competition, okay? Natural gas looks really good, and it's not surprising that's why natural gas is like one of the fastest growing power generation technologies in terms of new capacity additions. You notice that advanced combined cycle natural gas with carbon capture and storage is just a little bit more than nuclear. All right, so when you're looking at comparing ideas for nuclear with other carbon-free sources, this would be a good resource. Yeah?
Something that's, I think, interesting to point out the EIA doesn't do is conventional nuclear, that is stuff that China's building, like the designs that are proven to be safe as we're using them today, but that they're not really building anymore in the United States or elsewhere in Western nations, but in developing countries, they are still and will still be building these in 2020, and those make us a little closer to natural gas,
Okay.
but the EIA doesn't care.
That's good. I didn't dig into these numbers at all. I was just like, I'm gonna look at what the EIA is publishing, all right? So it's good to go, that's a good point, to understand what the assumptions are. Because policymakers are gonna look at these numbers without knowing what those assumptions are. And so it's important to know what those assumptions are if you're going to, if you wanna make the point that actually your innovation will not be that expensive, or to be able to compare on an apples to apples basis, essentially. Okay, I'm just gonna go through this spreadsheet that's available online. I found it's a spreadsheet that's easy to access, it's very simple, and I'm gonna do something that I've been told not to do a couple times, just go into Microsoft Excel in front of an audience, but I'm not gonna do really any calculations here. Or maybe I'll just do a couple back of the envelope calculations. But here are the assumptions and inputs for the levelized cost of electricity in this paper. All right, and I should mention that in table 1. Have any of you guys looked at this? I'm just curious. Okay, yeah. Starting with the summary page, this is a revised estimate from MIT. There was a MIT in 2003 published estimated cost for nuclear power, and then revised it, I guess, in 2007. I haven't gone into the details of this paper, but I want to sort of show you how I would look at this spreadsheet without knowing a whole lot about the assumptions used, and how I would just look at the numbers and use them to understand some of the big assumptions. So the levelized cost of electricity for nuclear is estimated at 8.4 cents per kilowatt hour in 2007 dollars. Okay, so if I wanted to convert that to 2016 dollars, I would use the consumer price index. Okay. Now let's go to the LCO inputs. You'll notice a lot of these line items match up with the NREL's simple levelized cost of electricity, right? So there is enough information in here to be able to plug it into that equation to figure it out. There's also more, right? So you're like, well, some of these, like, decommissioning cost isn't in the simple cost of electricity, like simple levelized cost of electricity. So, and they're all in different units, okay, which is kind of frustrating, all right? So I'm just gonna walk through each of these terms and just sort of go over and to make sure you guys have at least a very brief introduction to what those terms mean, okay? So capacity, what's capacity? I'm just gonna have you guys shout out what each of these are. Come on, I know somebody.
Total potential output.
Total potential output, okay? Capacity factor.
How often you can depend on your energy source to produce that amount of energy?
Depend, or in the case of a nuclear power plant,
Availability.
how often it's run.
Yeah.
Okay. So you know, for baseload power, it's like it's not a resource availability. It's how often you. Now, the reason it's 85%, that's a pretty common number for baseload power. 85 to 90, the highest. That's down for scheduled maintenance a lot of times. Heat rate. Does anybody know what the heat rate is?
Is that the amount of heat coming from your source of energy is then put through for the
That's the amount of energy you're using.
Oh, okay.
You know, usually, actually, I'm used to seeing. Oh yeah, okay, sorry. Yeah, so the heat rate is the amount of energy you're putting in to get out a kilowatt hour. If you flip that around, that's your thermal efficiency. Okay.
Could you repeat that one more time?
So your heat rate is basically, it's just energy in, right, for the unit of energy out, which is kilowatt hour. Okay. So if you flip that around, that's your thermal efficiency. Okay. So if another handy thing is BTU. I hate using BTUs. A good rule of thumb is what 1 BTU is 3,412 kilowatt hours. No, these are important numbers to know. I'm going to tell you, like, know how to convert BTUs into kilowatt hours. Okay, and I should know it. I think it's 3,412 BTUs per kilowatt hour. Pretty sure. I know because I've had to use that number many, many times, and it's a lot easier at some point to just know it than it is to have to calculate it. I also how many hours in a year?
260
Hours in a year.
8,760.
8,760. That's another number you should just memorize. Hours in a year. Okay. When you're converting how many kilowatt hours a year a plant produces, you just divide by the number of hours in a year, and you get your capacity factor. All right. A lot of these things, if you just keep some of these numbers in your head, it makes it very easy to just be able to put things in perspective, right, without having to pull out your calculator. Well, still, I can't do math in my head anymore. I always have to just do it in Excel. But overnight cost. What's overnight cost?
If you were to build it overnight.
If you were to build it overnight, so it's your CapEx. But without saying you have to have like a 5-year construction period. Okay, it's just like, again, it's sort of a levelized, it's a way of levelizing it to one time period. So you notice again that the capital cost here is expressed as a per kilowatt. Fixed O&M, is here. It's often you have when you're trying to estimate O&M, by the way, is operations and maintenance. Okay, so often the way that you'll estimate the operations and maintenance cost of a piece of equipment is just a fraction of its capital cost. So that's here. It's also, well, they do it per dollar per kilowatt per year, but the reason it's $1 per kilowatt is because it's a fraction of the capacity and not the box, right, and not the arrow going through. Variable O&M costs, notice that has a different unit because it's proportional to the actual production, right, not the capacity of the infrastructure to produce. Fuel costs on a BTU basis, million BTU basis. Waste fee also on a throughput basis. Decommissioning cost, carbon intensity. Okay, now we get into, these are the financial terms, okay? I won't go into inflation rate escalation. Don't worry about that. They're small numbers, yeah.
What's that unit on carbon intensity?
Kilograms of carbon per million BTU.
Okay.
Mm-hmm. I'm just gonna go tax rate. I won't talk about that. I'll talk about debt and equity. Okay, you might see these. These are the two ways you can finance. Sure.
Why is there no waste fee for coal?
Pardon?
Why is there no waste fee for coal? I mean, I know we're talking about nuclear waste as a fairly prominent issue in nuclear power, but coal produces a lot of ash as well, which does have to be disposed of. So there must be some cost to get rid of that.
I'm not familiar with that.
Okay.
It's usually accounted for the capital cost for carbon capture technology or for pollution technology, the retrofits, otherwise they're all considered capital because they don't care about it once it leaves their plant. And they'd rather not pay. They're not charged a fee, like we're actually charged a fee by the federal government of 1 cent per kilowatt hour.
Okay. It probably depends on the local. I guess that's a good point. This is a sort of a federal. No matter where you build it, you're gonna have to, or in the United States. Sure.
The decommissioning cost, is that non-discounted because it's quite high?
Well, here, these are the inputs. These are the assumptions without the financing costs. This is why that they've put the financing assumptions separate. They put, I believe, in the when they show. Well, you can pull this off the web easily, but the decommissioning costs are put at the end, and I believe they apply the discount rate, right? Unlike how you said, if you assume that the full cost of the decommissioning has to be considered as an upfront cost, which makes it more expensive.
Well, no, they still put the discount rate on. They just have to make sure that it's included in the cost.
It's in the cash flow the cash flow analysis that is in one of these tabs at the end. Okay. So who can tell me the difference between debt and equity? Yeah.
Debt is something that you would pay an interest on no matter what happens. Equity is some kind of ownership of what happens to the company.
Right. So there's two ways you can finance a project. One is you can borrow money and pay it back at a certain interest rate, and the other way is to actually finance it through ownership. You can distill a lot of these numbers into just two, okay, or three, like CapEx per year or depreciation, OpEx, and unit cost. But the important thing is you have to know how many kilowatt hours per year is put out, right? And you got to know the capacity factor. But it's cool because you can get to any one of those numbers if you just know a few. And that's the point I wanted to make here, is that don't be daunted by when you go into these things, because really they're all just components of those simple numbers. Okay, so any questions? Again, this is available online, so if if you guys want to understand more about the assumptions in there, I haven't read the paper that goes along with this, all right, so I can't explain why they use the assumptions they did. But it's laid out very nicely, so I recommend that that this is a good place to start if you want to understand what goes into estimating the cost of a power plant. Okay, so let's go back to okay, so I'm just going to go and talk about some tips for cost estimation. Now, I've shown you sort of how to look at other cost estimates, and so I'm just going to sort of review some best practices and a general approach towards estimating the cost of your idea, okay? So starting up with some tips, again, do it early. That's, again, something that we emphasize strongly at Cyclotron Road, is to not wait until you have perfect information or you've done this or that experiment. Plow forward through uncertainty. Just use a placeholder and keep moving and mark that as needs validation. Okay, because that asterisk line item might not be important at all. State your assumptions. It's fine to use educated guesses. Just say that you're using an educated guess and explain the logic behind that. So this is another thing like we find that a lot of times technical people don't do. I think you guys have probably heard about customer discovery at this point now, right? It's the same thing on the technical side. Go out and talk to people who have actually built these things or who have actually operated this equipment. You'll learn so much more than you will by trying to Google stuff or reading books. A lot of the things that you'll learn when you talk to people is you'll learn some of the things that are deal breakers, right? Like a piece of equipment has to be run under these conditions, or if the input material doesn't meet these quality standards, it's going to bust the whole thing, right? So they won't even talk to you if you can't meet these specifications, right? Okay, I say work from both ways. So bottom up and top down. The cost models that we encourage people to make are bottom up, which is based on the actual technical and physical parameters of the system, and then assigning basically cost numbers to that. But it's always helpful to every once in a while stop what you're doing and do a top-down estimate. So what do I mean by top-down? I guess an analogy that I was recently doing was thinking about how much I spent on food, right? In particular, I was thinking about the cost of making my son's lunch, right? And breakfast and dinner, because I hate having to make food and clean up. So I was like, how much am I spending on food, at a restaurant but how much does it actually cost me to buy that food and make it? So a bottom up estimate would be, okay, well, I have an egg and a piece of toast and with some jelly on it for breakfast. I'd be like, okay, well, how much does that piece of bread cost? How much does the butter cost? The jelly, right? And then, so doing meal. And then the top down would be going and looking at my bank statement for how much I spent at the grocery store, right? And then dividing it by the number of days in the month. And the same kind of bracketing approach is really helpful too when you're doing cost modeling. Start with the bottom up, but then do reality checks. Go and look at systems that are similar, and see if you're off by an order of magnitude, probably that's a flag, right? Or maybe not. Maybe you've come up with an innovation that is really game-changing in some part of the process. But it also helps validate your cost estimates when you go to the next step, and let's say you're raising money. To have two ways of calculating and getting to the same number makes your case a lot stronger. Finally, don't get discouraged. So a lot of the technologies at Cyclotron Road, and if you look at the cost of solar, for example, early on, this is going to be maybe 10 times more than that you estimate in cost than you can actually be economically viable. But if there's anything that I've learned from doing looking at clean energy technology costs is that they come down. The cost is not an intrinsic characteristic of the technology. It's something that reflects financing, it reflects supply chain, it reflects market conditions, but also design improvements contribute to cost reduction. So don't get discouraged. So again, I'm just going to go through the steps that you would do. But you have an idea. You have a factory or power plant. First thing you do, again, is come up with your bill of materials, particularly if you're making a product or a component, right? Let's say if you come up with some innovation that improves safety, right, or waste disposal, part of that supply chain. Then you come up with your process flow diagram. What does that process look like? The next thing you'll do is assign mass and energy flows to those processes. So quantify that arrow going through the box, okay? And then the next thing you'll do is assign cost values to the inputs and outputs and the pieces of equipment and the building, okay? And then once you've done those, then you can arrive at unit cost. And sort of put another way, the same steps. You start with what are the materials in the product? What's the process used to make it? So you do your process research to come up with your process flow diagram. To understand operating costs, you need to know the flow rates, input costs, and specifications for those processes. And then you'll have to do some market research and maybe some vendor research to get capital cost estimates. Now, for a lot of times for specialized equipment, you can't get a good estimate unless you talk to a vendor. But it's hard to get a vendor to spend the time coming up with a detailed cost estimate unless they really think you're going to buy it from them. So that sometimes can be tricky. But again, talking to people is often, if you're nice and you talk to people, you can get a lot more information in this area. We're all used to getting whatever information we want from the internet, but for this type of exercise, talking to people, a lot of this information is so esoteric, right? For this particular piece of equipment, it's just not published. And there's really no good reason for it to be published. So you have to talk to people to get, and as as there's anything that I've just demonstrated, the capital cost is critical, right? Not only because it's usually the larger fraction of the cost, but it's because capital cost is upfront cost and money now is more expensive than money spent later, okay? So know your CapEx. So you might hear the word techno-economic model. I try not to use that word a lot because it's sort of a mouthful, but it is what the class I'm teaching right now at Cyclotron Road is techno-economic cost modeling. And the reason that we talk about techno-economic cost modeling is because it couples the costs with the technical details of your innovation. And it allows you to modify the process specifications and the process design. And when I say it's a model, this is just an Excel model, okay? But the functionality of it is that it allows you to have some key inputs, and the outputs are cost and performance of your system. I just want you guys to sort of shout out the things that we know. Of course, that video didn't show all the information, but it's a good start. It's probably about the level of information that you could gather when you're doing your sort of first assessment of sort of back of the envelope calculation, right? So let's talk about the product design. What are some of the product specifications that you know from that video? And product specification is just like yellow. All right, so I'll start off yellow.
Hexagonal and woodwork.
Hexagonal.
Or round.
Or round. But for this pencil in particular, it's hexagonal. And I would say that the performance specifications of that would be doesn't roll off the table. Okay. What else?
Ferrules.
Ferrule, right? So brass right? Sort of in that would be bill of materials, right? So product specs would be, yes, it has a variable.
Some for a cylindrical core.
Okay, so we'll go forward, right?
Number 2.
All right, right, number 2, so that would be HB lead, okay? And then the, sort of the performance specification of that would be, it would be HB darkness or smoothness, right? Okay, so I think product specs is pretty simple. What's the bill of materials? This is also pretty simple.
The wood, the graphite, the lead.
Okay,
Or no lead.
so yeah, but what goes into the pencil? What goes into the pencil lead? There's 3 things. Okay, the bill of materials, remember, doesn't have the water in it. That's in the process. That's a process input. But yeah, it has graphite, clay, and wax. Okay, so that would be the bill of materials. What else? Cedar wood, synthetic rubber, or maybe it's real rubber. I don't think. Brass for the ferrule. I should also say product specs would be brand and print. Okay, so if this were on a whiteboard, I'd be writing this in all as you guys said it. How about equipment? What are some of the pieces of equipment that you noticed?
The lead cutters. Oh,
Let's start from the making of the lead and the wood.
Mixed tank.
All right, the ball mills, right? Okay. What else?
The cake presses.
The screw press and the die cutter.
Furnace.
The furnace. What else?
the conveyors that push everything
The
on.
conveyors, yeah. So that's a good point, right? Because a lot of times people do the equipment, they forget like the piping and the conveyor belts, all that auxiliary equipment, all right, is another line item that is often just a multiple of the piece of equipment.
Does do employees count?
Employees count as inputs. I'm talking pieces of equipment right now, yeah.
Does the building count?
Yeah, it does. The building and the land. I wouldn't call that equipment, but that goes in that category, right? It's CapEx. Let's see.
The thing to stamp.
The stamper, the painter, the sandwicher, the slab cutters, right? Okay, I think that's captures most of what we saw, right? Inputs, water, labor, what? Heat, right? So fuel.
The mixing stone,
So those would be the stones. Probably would be their inputs. They probably stay there. They're probably not moving through, but that might be considered part of the equipment. Okay, I think there was power, right? Okay, process parameters. So the ball mill operated for 24 hours. Like that's a parameter value, right? What are some of the other parameter values that were mentioned?
No air or oxygen can be in the.
Okay, I would say that's actually I'd say a constraint,
Oh.
right? So that like reject rate is a function of oxygen content. All right, the parameters I would say would be like a parameter associated with that might be that it has to operate for a certain time or temperature in order to avoid that, right? So the time speed is a parameter, right? So one thing that is fun to do, and sort of one of the things I'm trying to emphasize in this presentation is just doing back of the envelope calculations. You could see from the lead production or from a lot of the other steps too, it looked like it was about 5 per second. From that, you can make a couple assumptions and estimate the entire output of the factory over a day and over a year, okay? It's often you take the rate limiting step. The rate limiting step is usually, well, let me let you guys guess. What's usually the rate limiting step in a factory?
The slowest process of the factory.
It's the slowest, right? But it's often the most expensive piece, right? Because you're going to add cost or spend money to match. You don't want to be if you're going to spend all that money on one thing, you want to be operating it at maximum capacity, right? Whereas some of the other cheaper pieces of equipment, you might want to have a little bit extra capacity there, right? So that screw press and die cutter for the lead, it looked kind of expensive, right? Like, it was complicated. So I would estimate that might be one of the rate limiting step. And so if I said 5 per second, 5 pencils per second, you can estimate the output. Now, of course, you need to know what the capacity factor is, or the utilization of that plant. Can you guys guess what the output is of General Pencil? I don't expect you to know, but it's interesting to know. How many hours a day do you think the factory operates?
12.
24.
Okay,
Eight.
it's actually only 8 because the factory is really old. The demand for pencils is going down. Right, there's not enough demand to meet the capacity of that. They're barely staying in business.
And the guy also, he manually had to press the repair molds out.
Right, so you have to but if you're operating in a market where you can meet the demand for operating 24/7, you're going to do that, right? Because you need to pay back that capex, right? So a lot of factories operate, around the clock. They'll have multiple shifts for labor, and that's an important thing to know. And so an important thing to know that varies by location, right? Like labor laws and stuff. How often you can have people working is an important thing to consider. I called the factories like, how many shifts a day do you have? They're like, oh, just one. We operate 6 days a week, 8 hours a day. So from that information, I can I don't know how many pencils they produce here, but I can have a pretty good guess, I think.
What would your guess be?
5 per second times 8 hours a day. Although I'm sure that machine would have to stop, because they have to load it's still a batch process, right? Even though it's continuous on this end, it's still a batch process because each of those canisters has to be loaded one at a time. And then when that's done, they have to put a new canister in. So, maybe, 4 a second. But then again, that's assuming that's the rate limiting step and not like some other process that's downstream. What are some of the other process constraints that you noticed?
The crust on the
Right.
cake crust.
Right. So I would say the smoothness is a function of the dry time, right? That if it dries too long, then you're going to have you're not going to meet your performance specifications for smoothness, right? Those are the two main ones that I grabbed. What about, so performance specs, we did the smoothness of the lead, the darkness of the lead, doesn't roll. What else? It's under performance specification. That's important. And that it smells nice, okay?
Sharpening smoothly.
Right, straight grain. Okay, and then cost, we don't know the cost, we only know, they didn't talk about cost. We know from like going to the store about what the price of a pencil might be. You can look on Amazon and say, and create an upper bound on the cost based on what the lowest price you can find, right? So that's probably like 10 cents. Okay. So these are the steps that you would go through. This is sort of like the exercise you might go through when you're first looking at an idea, all right? And then you divide that into CapEx and OpEx, okay? So that's the end of my presentation. We still have 5 minutes left. If you guys have any questions, I'd be happy to talk about any of the things I just covered. Yeah?
I have a question. We were talking about this specifically from making a widget kind of perspective, but actually the thing that we're looking at is more of a broadly to call it a service, and looking at the kind of outline at the start is a bit more nuanced for that, because one of our big costs that we've identified is contracts, negotiations and signing contracts. I mean, with that kind of aspect, I mean, it might not be very interesting for everyone else because some people aren't necessarily doing that, so maybe we can talk about it later if you prefer, but I'm just wondering if you could say about how you apply these models to that kind of project?
Sure. Well, that would probably go into so the financial model includes like business costs as well, right? So transaction costs in contract negotiation. The other element of contract negotiation that's going to be important is the time that it's going to take, right, to actually start construction, because the longer delayed, that, that increases your cost because you have to start paying back. Yeah?
I'm interested, since you look at new energy technologies, when you have an item that hasn't ever been manufactured before and may need qualification or something that doesn't exist yet, how do you account for that? I mean, when you're going through unknown parameters, you try to make up fudge factors, or like how do you?
You mean, how do you estimate the parameters for processes that don't
Do you have
exist?
any examples?
I mean, I'd say in that case, there's always something that's similar, right? There's always an analog, and I would start by looking at something that's vaguely similar, and then understanding the cost component of that, and you know, again, I would sort of do a top down first, and then do a bottom up and check your assumptions. Are you thinking of a particular part of the process that's
I mean, an easy example for nuclear would be like if you have a new fuel type,
right?
you can't just look at the raw material cost and even how much it would cost to manufacture that. You have to look at all the qualification costs and everything like that. So I'm wondering if, like, you know, solar or wind or whatever,
Yeah,
there's.
they're new parameter values and constraints, and oftentimes the first people to do it are the ones that set the standards. So, I mean, in some ways you're at a disadvantage because you don't have something else to draw from, but you're also at an advantage because you get to be sort of standard setting first mover. Okay. Any other questions? All right.